In this paper, we present a new method named H2ONet for hand mesh reconstruction. Estimating 3D hand meshes from images is a fundamental task with multiple applications. However, achieving accurate reconstruction while being robust against occlusions and maintaining real-time speed remains challenging. Recently proposed Hand-Occlusion-and-Orientation-aware alleviates the occlusion problem. However, its formulation is implicit and ill-posed issue still exists when occlusion is severe. It inspires us to predict occlusion probabilities as guidance and use multiple frames to get extra information. Recon runs fast but doesn't take occlusions into consideration, so it requires additional design while preserving real-time speed. To this end, we propose our H2ONet, which consists of the dual-branch encoder, the hand mesh reconstruction and the hand orientation regression modules. Both the quantitative and qualitative comparisons demonstrate the effectiveness of our method. Existing research mainly focuses on three parts: single hand reconstruction, bimanual hands reconstruction, and hand object reconstruction. Depending on different scenarios, there are several different challenges, such as the reconstruction accuracy, the occlusion problem, the real-time inference speed, and the motion blur issue. In this paper, we mainly focus on the single hand reconstruction task and these three challenges. Recently proposed Hand-Occlusion-and-Orientation-aware alleviates the occlusion problem. However, its formulation is implicit and the ill-posed issue still exists when occlusion is severe. It inspires us to predict occlusion probabilities as guidance and use multiple frames to get extra information. Another method called Recon runs fast but doesn't take occlusions into consideration, so it requires additional designs to handle the occlusion issue while preserving real-time speed. As a commonly used representation, mono-coefficients disentangle the hand shape and orientation naturally. However, it is difficult to represent detailed gestures. Another approach is to regress the 3D vertices directly, which enables better alignment with input, but the hand orientation and shape are blended. To this end, we attempt to combine their advantages by disentangling the hand shape and orientation when regressing 3D vertices. Besides, the ill-posed issue occurs when occlusion is dominated in the input. A straightforward solution is to utilize multi-frame input to get extra information. So in order to better explore useful knowledge among frames, we make an assumption that the transformation among nearby frames is mostly rigid. The frame gap should be carefully chosen to obtain enough information and avoid breaking the assumption. First, we introduce the occlusion label preparation. Given a GT hand mesh, we render the hand mesh and the 2D vertices, where different fingers are distinguished by different colors. By masking the rendered hand using hand segmentation, we can remove occluded regions. Next, the occlusion state of each vertex is determined by checking the color consistency between the projected vertices and the masked hand. The finger is regarded as occluded if its number of occluded vertices is above a threshold. Finally, the hand is regarded as occluded only if all fingers are occluded. Then, we present the occlusion prediction process. The finger-level features are first fetched from the associated locations of the feature map and then fed into a multi-head classifier to predict the probability for each finger. The average accuracy on both datasets exceeds 90%. After that, we present our H2ONet. The input images are fed into the dual-branch encoder to extract general and task-specific features sequentially. Then, the hand mesh reconstruction module focuses on constructing hand meshes at the canonical pose, where the finger-level occlusion-aware feature fusion module is designed to utilize non-occluded information among frames guided by the finger-level occlusion probabilities. Finally, the hand orientation regression module estimates the global hand orientation, where the hand-level occlusion-aware feature fusion module is designed to alleviate the ill-posed issue using hand-level visibility. More specifically, multi-frame features are fused by weighted summation using associated occlusion probabilities as weights. Then, the predicted vertex offset is summed up with the original output. Following the same idea, the hand-level features are fused using the nearest enquiry strategy, which means the feature of the nearest non-occluded frame is fetched and concatenated with the current feature if the current frame is predicted as occluded. Then, the predicted hand orientation offset is mixed up with the original output. The quantitative results on two commonly used benchmarks show the SOTA performance of our method. Note that compared with Hand-Occlusion-and-Orientation-aware, our multi-frame version achieves higher accuracy and speed simultaneously. Though Mob Recon runs faster, our performance outperforms it by a considerable margin. Here we show some visual comparison between our method and previous SOTA approaches. We can see our method can handle severe occlusions caused by different objects. Here we show more results produced by our method on the DEX-YCB dataset. For each sample, from left to right are the original image, the cropped hand, the predicted result by our method, and the ground truth. Thank you for watching.